So this video is about the internal direct products. The previous video was about the external direct products, and now we are going to introduce the concept of internal direct products. Let us say we have a group G, and let us say that H and K are both subgroups of G. We define H internal direct product K, HK, we defined as HK elements, of course, such that H is in H and K is in K. Okay, let me give you an example, like U24. So the group of units module 24, set of integers less than 24 and relatively prime to 24 under multiplication module 24. So that will be 1, 5, 7, 11, 13, 17, 19 and 23. And now we take H. H is the set of the elements 1 and 17, and K the set with the elements 1, 13. It's always on U24, so the multiplication will always be module 24. So what is HK? HK will be 1 times 1, 1, 1 times 13, 13, 17 times 1, 17, and 70 times 13, 17 times module 24, 13 equals 5. Okay, so this is the first example of an internal direct product. So another example would be the symmetric group S3. I'm going to take H and K, two subgroups of S3. H will be, this is in cyclic notation, okay, the cycle of 1, this cycle 1 to 2, 2 to 1, so 3 stays the same, and the cycle of K, and the set K with the elements cycle 1 and cycle 1, 3. So the internal product HK will be this cycle times this cycle, we will get this one. This cycle times this cycle, we'll get this one. This one times this one, we'll get this one. And this times this one, we'll get this one. Okay. Now I just I rewrite that, since 1, 2, 1, 3 is 1, 2, 3. I rewrite that and I get this. Okay. So this is a second example of an internal direct product. Okay, so now we get into the definition of internal direct product of H and K. Let H and K be subgroups of a group G, so H and K are subgroups of G. We say G is the internal direct product of H and K, and we write it this way: J equals G equals HK. If 1, G equals the internal direct product of H and K, 2, HK equals key H for all H in subgroup H and all K in subgroup K, 3, H intersection K equals the identity. We say internal direct product of H and K if H and K are subgroups of G, and G is naturally isomorphic to the external direct product of H and K. Okay? Okay. I just wanted to leave here some sort of a visual idea of what's going on here. So we can say this is G, so this one would be H, this one would be K, and here we have the identity. Okay, so for the internal product, H and K must be subgroups of the same group. Okay, so now we give an example with D6, the dihedral group of order 12, and this F here, I'm going to call it it's a reflection. Okay, that will be a reflection. And here all these are rotations with k degrees. Okay, rotation 0, 120, 240, etc. So D6 is the external product of rotation 0, rotation 120, rotation 240, reflection, rotation 120 times reflection, rotation 240 times reflection, external, or in this case internal product, by rotation 0 and rotation 180 degrees. Okay, I said external before, this should be read internal. Okay, you can check that this if you call this one H and if you call this one K, it's easy to check that D6 equals HK, and so we say D6 equals it's the internal direct product, let us say HK, this here, if 1 D6 equals HK, 2 HK equals KH for all H in H and K in K, and 3 H intersect K equals, if you check the intersection of these two sets will be rotation 0, right? And rotation 0 in D6 is the identity. So yes, this is internal direct product. Okay, so this is a definition. At the end of the day, this is a quick generalization of the internal direct product. So definition, I would call it generalization of the internal direct product, H1, H2, Hn. So all these H's are subgroups of G. G is the internal direct product of H1, H2 to Hn. So G will be equal the internal product H1, H2, Hn for all these H's in Hi. So H1 will be in H1, H2 will be an element of H2, and Hn will be an element of Hn. 2. If all Hi, Hj equals Hj, Hi for all Hi in Hi and all Hj in Hj, of course with I different from J. And the intersection the direct product, the intersection with all this, with hi plus 1, should be equal to the identity, where I is going to be 1, 2, till n minus 1. Okay, so I leave here another theorem. H1, H2, Hn is isomorphic to the external direct product. So the internal direct product of H1 to Hn is isomorphic to the external direct product of H1 to Hn. If a group G is the internal direct product of subgroups H1, H2, Hn, so this case here, then G is isomorphic to the external direct product of H1, H2, Hn. It's a very nice proof, but I'm not going to do this now here. I can do it if that is requested or needed for some reason. So we get directly into the group of units module n has an internal and external direct product. So first let us take a k that is a divisor of n. We're going to write units module n k, units k module n, as x being an element of units module n, such that x equals 1 module k. A quick example: the unit module 7 of 105. Easy to check that it is 1, 8, 22, 29, 43, 64, 71 and 92. So it's easy to check that UK of n, units k module n, is a subgroup of the units module n. So this is a very important result from this theorem. The units module n as an internal and external, internal and external direct product. So we are going to write the units module n as an internal and external direct product. Suppose S and T are relatively prime. U of St is the internal direct product of US of St and UT of St. And UST is isomorphic to the external direct product of US and UT. And further, you can say that US of T isomorphic to UT and UT of St is isomorphic to US. So this is written this way: U of St equals US of St times UT of St, and that is isomorphic. So this is the internal direct product, and that is isomorphic to UT external direct product of UT US. The proof for this is really nice, but I'm not going to do it too. And this is a corollary of the theorem. M equals n1, n2, nk. The greatest common divisor of n, this is I, and I and j equals 1, where I is different from j. So the units module m equals um dividing n1 module m, dividing n2 module m, this is isomorphic to the external direct product of un1, un2 till unk. A quick example for this. Let us say u of 105. So u of 105 is going to be u15 times 7, right? So that is, according to the theorem, the units 15 of 105 times the units, now 7, unit 7 of 105. And that is what? That is the set of 1, 16, 31. You can check this, really easy. 46, 61, 76 from u 15 of 105 times 1, 8, 22, 29, 46, 43, 64, 71 and 92. Okay, and this is isomorphic of u7 external direct product of u15. Okay, but you can do this in a different way. For instance, now you can use these properties. U of 105, you can do, here we made 15 times 7, right? Let us do now 5 times 21. Okay, so that will be u units 5 of 105, right? Internal units 21 of 105. Okay, now you can check the sets for this, really, and they are 1, 11, 16, 26 till 101, really easy, times internal direct product of 1, 22, 46, 64, this other set, and that is isomorphic to u21, the group of units 21, external direct product of u5. You see, so units 105 equals units of 5 times 21, so that's an isomorphic to the units 21, external direct product of u5, or units 5, 105 times units internal direct product of u21, 105. Or you can factor u105 in 3, so that will be u of 3 times 5 times 7, right? So now you can do 5 times 7, 35, so u35 of 105, 3 times 7, 21, u of 21, 25, and the last one 3 times 5, u of 15, so it will be u35 of 105 internal product, u21 of 105 internal product, u15 of 105, and that is isomorphic to the external direct product of u3, u5, u7. You can use these theorems to solve those problems that you see a lot on the internet, and this sort of questions that basic mathematics they like a lot, and especially kids, they like a lot this sort of number theory basic problems. So determine the last two digits of 49 to the power of 111. Well, you look at this and you immediately observe that we are searching for a value module 100, right? And it's easy to check that 49 will be an element in the units, the group of units module 100. Okay, but now you use the previous theorems. So you get units module 100. You check that that is isomorphic to U4 external product 25, right? 25, yes. 4 times 25. That is isomorphic to, for instance, Z2 external product Z20, right? So x to the power of 20 will be 1. Well, this is for all x in U100. Okay, so 49 to the power of 111 will be, of course, module 100. We are talking about module 100. 49 to the power of 20, right? To the power of 5 times 49 to the power of 11. Okay, so this disappears, module 100, that's 1. So this 49 to the power of 11. But 7 times 7, 49, so 7 squared to the power of 11. That's 7 to the power of 22. But what is 7 to the power of 22? Is 7 to the power of 20 times 7 to the power of 2. Okay, and since this is 1, this will be 7 squared, and that's 49. Okay, so those are the last 2 digits of 49 to the power of 111.